We're going to skip all of that. If you want to do it, my website is here. You've got 5, 4, 3, 2, 1. Anyways, about this talk. This is a broad attack or an interpretation of what my research project is going to be. If you saw the logos at the start, it has some funding from ARIA, it is based in Cambridge, UK, and hopefully nothing is set in stone. If you have strong objections, both philosophical, moral, ethical, or matters of taste, do let me know. And we will start with a model of AI and learning and end with the core questions of my project and some projections looking forward. There will be 3 sections, each with 2 inspirational quotes, which I will not explain for lack of time, and a final roundup at the end where there will be a quiz. All right, let's begin. The first quote is from Francis Drake, "From small things, then great things." So this is about course grading and the overall worldview of how AIs might learn and how humans definitely do seem to learn. The second quote, I do not have time. All right, let's start with a 2D particle model. Let's say that we have some particles on a board. The particles are in a 2D plane. They can attract and repel each other. So, looking at this picture, how would we predict what will happen to this picture in the next second? The question is very simple, right? We have particles. So, each particle has forces, as we've described. They attract and repel. So, if we can just do a microscale calculation of every single particle at every second, we will know definitively what it will look like the next second. However, that is not how human brains work, mostly because we don't actually have the ability to do matrix calculations. What we do maybe instinctively is we say, yes, we'll start to clump them together, right? Particles that kind of lump together, they're close by, so we'll kind of like group them, and we kind of try and track them across time as they sort of like move around, and we try and see whether like this sort of like geographical clumping does anything. So we might imagine that there are now forces between these blobs. Effectively, we are constructing a model of these particles where, like, instead of modeling each individual particle, we turn them into little groups and we model them. And of course, we can make groups of groups, so we can turn the little stripy bits of the particles into a bigger group, and then we can just say, yes, this is obviously a blob. A blob interacts with the blobs next to it. And so now we have a much simpler, so there are thousands of particles. We've gotten down to like maybe like 15 blobs, and the blobs kind of blob around. And that gives us coarse graining. What I've described, of course, is a model in space. So we divide space into shapes, into objects, into clusters. There are also models in time. You are familiar with these. These are called Markov processes. They are, instead of each point being a point in space, each point is a point in time, and you move along the states forward and backwards. And then in 1920, Albert Einstein discovered space-time, which is Markov blanket. So if you are familiar with axiom inference, you know these. The idea is that we can fence off certain areas of Markov spaces so that like all inputs and outputs go through this sort of blanket. So you and I are surrounded by a blanket, usually called skin. So what happens is we sort of like merge them, right? Objects that are close together in space affect each other in time. So we can kind of do a sort of this merger thing, and from there we get axiom inference and a bunch of other theories that I don't really have time to summarize. The rules of the game. How do we do this in a way that actually makes sense and does not just mean that I took these points and I drew a circle around them and therefore they are mine? We start with a system, so we have states, variables. Usually Eric Cole, whose paper I'm shamelessly putting off, calls them states in the Markov chain. And then we can say that some of these states are events. So if we have 2 states, raining, floor is wet, the wet is an event, and then we can assign causes to events. So it's raining, then it's wet. So then we say that the sufficiency is merely the conditional probability. Given that it is raining, how likely is it that the floor is wet? Probably pretty high. The necessity is, what are all the other ways the floor could end up wet? Someone could have sprayed it with a garden hose, someone could have spilled their drink, right? There are so many other causes that we have to create this second sort of tracker. The first one is, given it's raining, how likely is it wet? The second is, given it's wet, how likely did anything besides rain cause it? So the only way the floor can be wet is raining, and the floor is wet, we can be pretty sure it's raining. All right, so to coarse grain, we can just take some of these little states here, these little states where you can imagine little clumps, and we bind them together into a macro state. So we can imagine that the raining and the floor being wet, if there was a 100% correlation, we would just group them together and we say raining, therefore floor wet, therefore we have 100% causal reduction, and we keep all the explainability in the system. We can still track everything that happens, just because we know with absolute certainty that these are combined. Here's another QR code. This is a great paper, by the way, extremely readable. The maths doesn't get any harder than this. So basically, what we call coarse graining. Most people also call modeling dimensionality reduction. Every field comes up with its own term. I think in English it's called a metaphor. You reduce the number of microstates while improving the certainty about macro-scale causation. Instead of tracking each water particle, you now track the state raining, which sort of combines all of the individual water particle states into one metastate called raining, and we can still use it to make inferences about our environment. Modeling can of course be iterative. We can turn local clouds into bigger clouds, into even bigger clouds, and we can say, oh yes, it's raining across New York, which of course really means there are like 20, 30, maybe 100 clouds, each individually pouring rain across New York. We can collapse it even further, so that's hierarchical modeling. And what the causal emergence says is if you can find ways to create these models that at each step improve predictability of the whole system, then an optimal hierarchical model exists. You can walk up a gradient. The word gradient has been mentioned. The problem, of course, is that these sort of very, very simple toy models look to us, all right, here are the dynamics of these two things. We can do the coarse grading, we can do all the tricks that we've just learned. Yes, there are two triangle clumps, and we can bind them together in time. Very good. Unfortunately, real life is slightly more complicated. Here are two more RGB tensors. They are two images. To make any sense of these, you would need a very good idea of how humans work in 3D and all sorts of other concepts. If you only tracked the dynamics of these pixels, you would get nowhere. Which means, of course, that even if you manage to create a summary tensor of all basketball playing videos, reality does often create surprises that don't conform with your sort of general expectations. A machine learning model would probably just classify this as another basketball player, which would be wrong. So the question is, so IRL data is creating these shallow spatial temporal snapshots of incredibly deep processes. So instead of finite state automata or Turing machines, we use psychology, physics, chemistry, or biology as generator functions. There are literally billions of possible causes and very, very messy causal chains. The last time someone tried to do a coarse grading of history, we got The Decline and Fall of the Roman Empire by Edward Gibbons. If anyone's read all 6 volumes, let me know. So is there any way of relating this to human and machine learning? Part 2. So blah, 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 Christopher Marlowe. That's actually not Christopher Marlowe, that's still Francis Drake. So we're going to do some Photoshop. There we go. All right, so spatial coarse grading in humans. Humans turn pictures like this into, so we see a pipe, we can imagine what it would look like in 3D, we can turn it around in our heads, we automatically assign it the status of a 3D object. This is in fact not a pipe. If we take those little broken circles, we can call them a broken circle instead of individual pixels, right? We do all of these things that we mentioned sort of in the abstract earlier on, automatically every day in our lives. When I look at that chair over there, I can't actually see the bottom of the chair, but I can auto-fill in the bottom of the chair. So we actually know that like humans do a lot of this sort of coarse grading modeling stuff automatically in their lives. ANNs actually also do this. So the big breakthrough in CNNs, of course, is the idea that we can do the hierarchical coarse grading. We just force it to reduce the dimensionality at every step. And we know that it detects edges, that it detects objects, it detects like features. These are like fairly well-established principles of computer science. Unfortunately, humans also learn to temporally coarse grade. This is the Marvel Cinematic Universe. We have taken data points, which are individual movies, and we have assigned them into a causal ordering. We have reduced the total amount of information in the system, and we're still keeping everything sort of in a knowable order. Animals can also learn to temporally coarse grade. This is Ivan Pavlov, his famous experiments with the dogs. So you can teach them to bind causal events together in time. Bell salivates, right? So effectively, that's called Pluto's cave. RNNs and transformers also track temporal dynamics. And of course, and here's some interesting new research. So as models get stronger, so you can see that the alignment, language and visual alignment between the embeddings for words like cat and pictures of cats actually increases. And you can reverse engineer embedding spaces. And in fact, we know that as training increases, the amount of parameters used per model, i.e. the simplicity of the model, increases over time. So one of these lines, which you can't see, is actually 3.6% of the original model's parameters, and it still pays basically the same after training. This is a lottery ticket hypothesis, and this is my favorite paper, Human Brain Alignment in the Wild. So when we talk, we use speech embeddings, and there are linear mappings that we can learn. And when we speak, we use language embeddings. So from AI to human, we can draw linear mappings, and there are strong correlations. The part 3, blah, blah, blah. So that's just my research project. This is my research project link and the bibliography. Just scan that, it'll be fine. I think I'm now well and truly out of time. I got the worldview across. I don't think I got any of my own original research. So we're going to pass that back to Waitan. How many seconds do I have left?
You can have, well, until the lightning talk person arrives here.
Okay, sure. In which case, the only thing that's left to say is hot takes. Machine intelligences do learn like human intelligences. The gap between human learning and machine learning is not that large. It mostly comes from offline learning versus online learning. And we know this because we have a hierarchical reasoning model that has just beaten RKGI2, came out yesterday, with brain-like architecture and 26 million parameters and no online training, and just online training. It's just 2 RNNs and a trench coat. If you want, there's some reason for optimism, but we won't get into them. Talk to me if you want. Thank you.